Okay, today's lesson will be on projectile motion. I'm going to try to break this into two videos, one more or less on the theory and conceptual examples, and then one more on more or less the mathematical examples. So here we go. So what is projectile motion? Basically, it's motion of an object in two directions. It has to be under the influence of gravity, and it has to be moving in the x direction as well. We assume its shape is a parabola or a portion of a parabola, and it's free fall in the y, and in the x direction is constant. So we assume there's no no friction. Obviously it has to be gravity. Alright, so let's look at the horizontal direction first. If there's no friction, therefore there's no force acting on it. And if there's no force acting on it, it's not going to accelerate. And if it doesn't accelerate, the velocity is going to remain constant. And if the velocity remains constant, the only equation we really have is simply velocity is equal to displacement over time. Okay, we could use all the following equations I'm going to show you in a second for constant acceleration. But if this constant acceleration actually is zero, then they all reduce down to either common sense or the following equation, velocity is equal to displacement over time. So let's look at them individually. If you look at this equation, the final velocity is equal to the initial velocity plus acceleration times time. If the acceleration is zero, then the final velocity is equal to the initial velocity, which is, well, common sense. Nothing happened. And if you look at the next one, the final position is equal to 1/2 the initial plus the final velocity times time. Basically, if you add these two together and divide by 2, it comes out to just the initial velocity because the velocity is not changing. So once again, it reduces back down to this equation. And the same thing is true here. If this is 0 here, the acceleration is 0, then this part of the equation is simply this. And this is another one of those common sense ideas that if the acceleration is 0, then the final velocity squared is equal to initial velocity squared. So the book tends to do problems in the x direction, and they use these equations and then just say the x is 0. And so that parts of the equation drop out. I'll try to do both ways, but I tend to like this idea better and just use the simplified version. Okay? And in the y direction, or the vertical direction, the object is unsupported. Therefore, it accelerates due to gravity. And since gravity is a constant acceleration, you therefore must use the constant acceleration equations. Okay? And when you use these constant acceleration equations, notice that the a can be replaced with gravity, the gravitational constant. Okay. So how are the x and y related? They're related through the time of travel. And it's kind of common sense. An object can only fall in the vertical direction, y direction, as long as it's in the air. An object can only travel downrange in the x direction until the ground comes up and hits it. So they're really related through the time of flight. Okay, here's a quick mini lab to try at home. You line up 3 pennies on the edge of a desk or table. You hit the 3 pennies simultaneously, so the pennies are hit with different forces as shown below. Alright, so here's the top view. You have 3 pennies all lined up at the edge. Take a ruler and you whack them. So they all leave the table at the same exact instant. But obviously this one will be hit with a harder force, so it should have a larger velocity x, while the one closest to the pivot point here will have the smallest force. And what you're going to try to do is note the sound of the pennies hitting the floor. Okay? So why don't you pause the video now, give it a shot, and then come back. Alright, what you should have noticed is that there's only one sound. They all hit the ground at the same time, so the velocity of the x has nothing to do with falling in the y. And you're going to say to yourself, sure, it works for pennies, but would it really work for like a rifle being shot? Yeah, it's the same thing, but only faster. Shoot a gun horizontally at the same instant you drop a bullet. And they have to be from identical heights, and you have to have the gun completely horizontal, and you can't worry about the earth curving and stuff like that. Do the bullets have the same vertical distance to fall? Yes, they do. So therefore, they should take the same time to fall. Next question comes up. But the bullet will travel a long distance without falling much, the one that's shot. And that's true. It will have a very large horizontal distance, but it will take the same amount of time to fall. So the one that's shot may end up being a half-mile away, but it should still take the same amount of time to fall as the one that was dropped. All right. Here's a gun test that we can do, and I'll show you this demonstration in class, but here's a picture I wanted to show to you. This red ball was dropped at the same instant the yellow ball was hit. And this was done with a camera shutter that was left open and a strobe light was used. And the whole idea behind this is that you can actually see the free fall motion. And you see how it gets further and further and further and further apart, as it should in free fall. But this one was shot, the yellow one was shot horizontally, but yet it still falls the same vertical distance on the way down. Notice that they stay right next to each other. Okay? So the initial velocity in the x has nothing at all to do with falling in the y. They could be treated completely independent of each other. And another interesting thing to see here is if you took the horizontal distance that each of these traveled, they did stay constant, didn't they? Okay? All right. Here's a little conceptual problem you want to ask yourself. Suppose you're driving a convertible with the top down. The car is moving to the right at a constant velocity. You point a rifle straight up in the air and fire it. Now we're going to assume there's no air friction. Will the bullet land behind you, ahead of you, or in the barrel of the rifle, like fall right back in the barrel of the rifle? Well, obviously not going to fall right back in the barrel of the rifle. It would be too hard to do. But is it going to land behind you, in front of you, or back in the car? So what do you think? Here's the answer. Should end up falling right back in the car. Just because the bullet is going up has nothing to do with the initial velocity of the bullet, which was the same as the car. It should go up at the same time it's going to the right, and it should fall right back into the car. All right? Here's another way of thinking of it. Let's say you initially shoot or throw a ball, in this case 30 meters per second upwards, and at the same instant you're throwing it 5 meters per second to the right. So in other words, we took the initial velocity, whatever that was, and broke it into its vertical and horizontal components. And for this case, I'm going to use gravity as being 10, okay? Because it just would make it easier. So what I'd like to do is think to myself, what is going to be the velocity in the y direction in each of these boxes, and the velocity in the x direction in each of these cases on the way back down? And a matter of fact, a couple of these I can fill in as well. How am I going to find the resultant velocities? All right, so take a moment, pause the video, think to yourself of what you think these answers should be. Okay? All right, we're back. So, hopefully this is what you got. In the y direction, it's reduced by 10 meters per second every single second, just like free fall. So on the top, it's 0, and back down, it's -10, -20, -30. But the key idea here too is to look at this x direction did not change. It remained at 5 meters per second. So, think about it this way. How long did it actually take to go up? Well, 3 seconds. How long did it take to go down? 3 seconds. See the symmetry in these problems? Okay. Another thing to do is you can easily calculate the range of problems like this. Okay? So if you look at this, it's up, going up for 3 seconds, down for 3 seconds, so it's in the air for 6 seconds. So how far downrange will it go? Well, it has nothing to do with the y direction other than the time of flight. And we could determine the time of flight from the y direction because it took 3 seconds to go up and 3 seconds to come back down. So it's in the air for a total of 6 seconds. So it's in the air for a total of 6 seconds. How far in the x direction could we travel in that time period? Well, velocity is equal to distance over time, or distance is equal to velocity times time. So that would be 5 meters per second times 6 seconds. So it should end up being 30 meters downrange. All right. How high should it reach? Well, there are equations we can use, but we should think of it from a common sense point of view too. Some numbers that you remember from previous lectures is how far will any object fall in 1 second? Okay, has nothing to do with going in the x direction. Only how far will it fall in 1 second? Well, think of it logically. The velocity up here is 0. The velocity here is 10. Half that velocity, or the average velocity, is 5 meters per second. So how far will any object fall in 1 second at a speed of 5 meters per second? Should fall 5 meters. And then the next unit going down, you have a speed of -10 and 0. This could be -10 and -20. The average speed would be 15. So how far should it fall in the next section? At 15 meters per second. Should fall another 15 meters plus the initial 5 meters. So now you're 20. Remember how we did this in the last section. So how high is this? Well, in the first second it fell 5. Second it fell 20. Third second it fell 45. So this should be about 45 meters tall. Okay? All right, so moving on. Okay, from the top of a cliff, a person throws 2 stones. The stones have identical speeds, but stone 1 is thrown downward at some angle, and stone 2 is thrown upwards at the same angle. Neglecting air friction, which stone, if either, strike the water with a greater velocity? As you can see from this picture, it's kind of obvious. The one that was thrown upwards will travel up to some maximum height where it has 0 velocity in the y, but the same velocity in the x, and it will come back down to point P. At point P, it's the same exact thing as the initial position. The same angle, but just delayed. So how will the speeds compare from 1 to 2? The speeds when it hits the ground should be exactly the same. The difference between 1 and 2 is 2 has to go up first and then come back down. So it will just take longer to get to that same speed. And it should land further away, obviously. Okay?